So in this video, we'll be talking about degree sequence. And when talking about the degree sequence, I'll be introducing the Handshaking Lemma and the Havel Hakimi algorithm. So first, let me introduce or quickly define what is a graph. So a graph is essentially a collection of vertices and edges. For example, this is a graph, and I'm kind of writing the edges first, and then I'll be connecting them with edges for some of the vertices. So this is a graph, and it has 4 vertices and it has 4 edges. A concept related to vertex is called degree. And degree of a vertex is essentially the number of edges touching a vertex. So in this example here, these vertices have degree 2, 2, 3, and 1. So a degree is simply just a concept or a property of each vertex. But when you kind of combine all the degrees together, you achieve what is called the degree sequence. So a degree sequence is just a list of degrees of all the vertices. And in this example here, this graph has degree sequence 1, 2, 2, 3, and we take the convention that you list the degrees in non-decreasing order. So now let's think about a question, which is there a graph whose degree sequence is, let's say, 1, 1, and 1? Okay. You can try a little bit, and you'll soon see that the answer to this question should be no. And the reason that this is no can be shown through what is called the handshaking lemma. And what the handshaking lemma says is that the sum of degrees of all vertices equals to 2 times the number of edges. Okay. Here's kind of like a quick proof of the lemma. So let's just focus on one edge in your graph. Okay. When you're summing up the degrees, this endpoint is counted once, and this endpoint is also counted once. So this edge essentially is counted twice. So that's all the proof we have here. We can quickly check this on our graph above. For example, here, the degrees sum up to be, let's see, 8, which is exactly 2 times 4, and 4 is the number of edges of the graph. Cool. Now let's look at a little bit more complicated degree sequence, and let me write it here. So the question here is if there's a graph whose degree sequence is this. So I'll be trying to construct a graph whose degree sequence is exactly this. And when I'm trying to do this, I'll be following a particular procedure. So I'll always pick the vertex with the highest degree. And in this case, the degree is 8. And I'll be connecting this vertex to the 8 vertices that have the largest degrees from the remaining vertices. So in this case, it will be all these vertices. Okay. So let's give them a name, all the vertices. Let's call this V1, call this V2, so on and so forth, and we call the last one V10. So let's try to construct a graph now. Here's V10, and then we have V9 here, and so on and so forth until we have V2 here. Okay. So this is part of the graph. Now we're going to update the degree sequence to reflect that we already done part of the graph. So this is all done. So all of them is satisfied. And we still need 5 more edges coming out of V9. And similarly, all these numbers will be 1 less. Okay. Now we'll repeat the same type of procedure. We'll start with the vertex with the largest degree, and we're connected to like 5 vertices with the largest remaining degree. Okay, so V9 will be connecting to these. Okay. Once we've done this, we can update the degree again. So 5 is gone. All the other ones will be 1 less. Okay. Again, we'll pick the one with the highest degree, and they'll be connected to these two. Okay. And updating the degrees. And then lastly, the vertex with the highest degree is this one, and you really only have 1 left, and we'll just be connecting this to vertex 1, which is not even connected to anything yet. Okay. So just by constructing the graph, we know that graph whose degree sequence is exactly this. Okay. So what I demonstrated here is actually what is called the Havel Hakimi algorithm. What is good about its algorithm is that if this degree sequence actually works, then following this procedure will always give you a graph whose degree sequence is what you want. And also, if there's no graph that has the degree sequence that you're looking at, then this procedure will always fail to construct a graph. Which means is that whenever you follow the algorithm, if you're not able to find a graph, all it tells you is that there's actually no graph that have the given degree sequence. Okay, that's it for now.